Hello, I am Jasmine Trammell in Chemistry 131 Section C, and here's my Module 2 project on chemistry concepts. First, I'm going to talk about electromagnetic radiation. It is a form of energy that travels through space as waves. It is made up of electric and magnetic fields that move together in a wave-like pattern. These waves travel at the speed of light of 3.0 times 10 to the 8th meters per second. For example 1, we're going to talk about visible light. Visible light is the portion of electromagnetic radiation that we can see. In the picture below, you can see that the human eye can detect from roughly 400 nanometers, which is violet, to 700 nanometers, which is red, in wavelength. Sunlight contains all the wavelengths of visible light, which combine together to appear white. When sunlight passes through a prism or droplets of water in the air, it separates into individual colors, forming a spectrum. The spectrum, of course, is red, orange, yellow, green, blue, indigo, and violet. This separation occurs because each color has a different wavelength, and therefore it bends or refracts at a slightly different angle. For example 2, we're going to work on a conceptual problem. The question states, the wavelength of a radio wave is much longer than that of visible light. What does this tell you about its frequency and energy compared to visible light? To answer that question, we'll need to know the wave equation for electromagnetic radiation. The equation will be c, which is the speed of light, equals wavelength times frequency. Since c is a constant at the speed of light of 3.0 times 10 to the 8th meters per second, then wavelength and frequency move at opposite directions. This means that if wavelength is getting longer, then frequency is getting shorter. So the wavelength will look something like this. You can see that the one with lower frequency has a longer wavelength, and the one with high frequency has a shorter wavelength. Since radio waves have a longer wavelength than visible light, then the frequency of this will be shorter than that of visible light, because visible light has way more frequency. Because radio waves have such low frequency, each radio photon carries way less energy. In fact, visible light photons have millions to billions of times more energy than radio photons. For example 3, we're going to do an equation problem. The question states, a photon has an energy of 3.2 times 10 to the power of 19 joules. What is its frequency and wavelength? So we'll need two formulas to solve this equation. This formula right here relates energy to frequency. H in this formula equals Planck's constant, which equals 6.63 times 10 to the negative 34th power of joules. Once we find the frequency, we'll then use this. Let's start by rearranging the energy equation to solve for the frequency. So you want to put F, since you're solving for F, which will equal energy over Planck's constant. Now we're going to substitute the numbers in, so we're going to do frequency equals the energy, this is the energy, and we're going to put over Planck's constant, which is 6.63 3 times 10 to 34th, and then negative 34th. So when dividing numbers in scientific notation, we divide the mantisas and subtract the exponents. Therefore, we do 3.2 divided by 6.63. And we put this in the calculator, it'll give us approximately 0.4825. Now we want to subtract the exponents. So you want to do negative 19 minus negative 34, and that'll equal 15. So now that we have that, we're going to combine these together, and now it will be 0.4825 times 10 to 15 hertz. Because we usually keep the mantises in between 1 and 10, I'll move the decimal point in here one place to the right. So now it'll be 4.825 times 10 to the 14. So this is the frequency of the photon, which is typical for visible light in the range of orange and red light. Now we're going to find the wavelength using this equation that we had earlier. So we know that the speed of light is this equation, and we know that our frequency equals to 4.825 times 10 to the 14. So now we're going to plug that into this equation. So we're going to do, so now that we plug this into here and this into here, we will then again divide the mantises. So we'll divide the mantises and we'll get an approximate. So let me actually do that. An approximate of 0.6219. Like that. Then you want to do exponent subtraction. So you do 8 minus 14. 14. And that'll equal negative 6. So now I've combined them and I put them in the formula, but obviously you want to keep the mantises in between 1 and 10. So we're gonna move this decimal to the right once. And by moving the decimal one place to the right, it also adds 1 to the exponent. Since we're working with visible light, we want to convert the meters to nanometers. We know there are 1 times 10 to the 9th nanometers in a meter. So we multiply by 10 to the 9th. So we're just gonna make this easier and just do 6.219 times 10 negative 7 plus 9. Then we add the exponents up. That's gonna equal 2. So it'll be 6.219 times 10 to the second nanometers. And since we know that 10 to the second equals 100, we will move 6.219. We will move this 2 places, and then that'll equal 6 to 1.9 nanometers. So if we round this, we'll get 622 nanometers, and that is the wavelength. there. Electromagnetic radiation plays a key role in nursing through its chemical interactions with matter. X-rays help create medical images that pass through tissues based on atomic composition. UV light also works as a disinfectant to break down microbial DNA bonds. Infrared light provides therapeutic heat. Nurses also use visible light in devices like pulse oximeters, which measures oxygen levels through light absorption differences. Now we're going to be talking about wave and energy equations. Wave and energy equations describe how light and energy travel as waves. Here is the wave equation and here is the energy equation. When we combine the wave equation and the energy equation, we get this, and we see that shorter wavelengths have higher energy levels. These ideas help explain how different types of electromagnetic radiation, from visible light to X-rays, behave and affect matter. In our first example, it gives us a frequency of 4.8 times 10 to the 14th power, and it wants us to find a wavelength and photon energy. Our first step is to plug the numbers into here. So we know that the speed of light is 3.00 times 10 to the 8th meters per second, and we know we have the frequency 4.8 times 10 to the 14th. Now we're going to divide our mantises. So we're going to do 3.0 divided by 4.8. In our calculator, this will give us an approximate of 0.625. Now we will subtract 8 minus 14, and we will get negative 6. We will then combine the two, so we will do 0.625 times 10 to the negative 6. Then we always want to move this decimal to the right to convert it to scientific form, standard scientific form. With that being said, this will now turn into 6.25 times 10 to the negative 7. Therefore, the frequency 4.8 times 10 to the 14th hertz photon has a wavelength of 6.25 times 10 to the negative 7, or that'll equal to 625 nanometers. Now that we've found the wavelength, we now have to find the photon energy. For this, we want to plug in our given, and we know that Planck's constant is 6.63 times 10 to the negative 34 joules. And our given frequency is 4.8 times 10 to the 14th hertz. We then want to multiply the mantises. So we do 6.63 times 4.8, which in the calculator will give us 31.824. Then you want to add the exponents, and this is the number you get, and now you want to combine them. So now you combine 31.824 to the exponent, and since this mantissa is not in between 1 and 10 but greater, we're going to move this to the left. So now it's going to be 3.1824, and we're going to subtract 1 from 20, so that'll be like that. And therefore, the energy of the photon equals this. For example 2, they give us the X-ray wavelength of 1.0 times 10 to the negative 10th, and they want us to find photon energy and express joules and electron volts. For this equation, we're going to use this formula. So we know the formula for Planck's constant is 6.63 times 10 to the negative 34. And we know that the speed of light is 3.00 times 10 to the 8th. And now we're going to put that over the wavelength of 1.0 times 10 to the negative 10th. First, we're going to multiply the mantises, so we do 6.63 times 3.00. That'll give us 19.89, and now we want to add the exponents. So we do negative 34 plus 8, and we get 26, negative 26. So therefore, this equals and like always, we want to move this to the left because that's greater than 1 and 10. So we want to keep that less than, so we do 1.989 times 10 25th. Now we need to divide the wavelength, which is this. So we're just gonna do the mantises. We're gonna do 1.989 divided by 1.0, and in our calculator, we're just gonna get 1.989. As always, we want to subtract the exponents. And we're gonna get negative 15. Therefore, our photon energy equals 1.989 times 10 to now we want to convert to electron volts from the problem. We're going to do energy over the electron volt formula, which is 1.602 times 10 to the negative 19. Then you want to divide the mantises. And you want to subtract the exponents, which energy will give you 1.24 times 10 to the 4th. And electron volts will give you 12.4. Therefore, an X-ray with this wavelength has about 1.99 times 10 to the negative 15th joules in energy, and it has about 12.4 kilo electron volts. For example 3, we're given microwave frequency, which is 2.45 times 10 to the 9th hertz. They want us to find the wavelength and the photon energy. Since we're finding wavelength, we're just going to plug in the numbers that we know. So we know that the c of speed of light is 3.0 times 10 to the 8th. And we have our frequency, 2.45 times 10 to the 9th. Now you want to divide the mantises, so 0. And put that in our calculator, and it gives us 1.22448898. Then we subtract those exponents, and we get 10 to the negative 1. Now if we do the math, that'll give us 0.122448898 meters, which can also equal 12.2 centimeters. Now to find photon energy, we're going to need this equation. So we just plug that in and we do Planck's constant times the frequency. Multiply the mantises. Equals 16.2435. Add the exponents. And that'll give us 10 to the negative 25. Now we combine everything together. Then we want to move this decimal over to convert it to standard form. Now we want to convert to electron volts, so we do 1.62435 times 10 to the negative 24 over 1.602 times 10 to the negative 19. Keep in mind this is the formula for electron volt. Now our approximate will be 1.014 times 10 to the negative 5. Given that, our photon energy equals 1.62 times 10 to the negative 24 from right here, or, and joules of course, or it equals 1.01 times 10 to the negative 5th meter. Therefore, a 2.45 gigahertz microwave has a wavelength of around 0.122 meters or 12.2 centimeters, and each microwave photon carries only about 1 times 10 to the negative 5th eV. Nurses see these equations in action every day. X-rays use short wavelengths and high energy to create internal body images. MRI machines use longer wavelengths and lower energy radio waves, which are safer for soft tissues. Understanding the relationship between energy and wavelength and frequency helps nurses appreciate how medical imaging and treatments actually work. Now I'm going to talk about topic 3, which is quantum numbers. Quantum numbers describe the location and behavior of electrons. It's basically like looking for a house address. Quantum numbers help chemists locate an electron within an atom structure. There are 4 quantum numbers, and each one gives us a different piece of information about the electron's location. The first number, n, is the principal quantum number. N tells us the main energy level or shell where the electron is found. The second quantum number, angular momentum, is L. L describes the shape of an orbital, basically how an electron cloud looks. Third, we have magnetic quantum number, ML. ML tells us the orientation of the orbital in 3D space. The fourth orbital is the spin quantum number, MS. MS represents the spin of the electron, whether it's positive half, 1/2, or negative half. For our first example, we're going to look at hydrogen. Hydrogen has 1 electron, meaning it has 1 s orbital. From that information, we can find the quantum number. For quantum number n, the energy level is 1. This is because hydrogen only has 1 electron. For quantum number L, its orbital shape is 0. This is because it's an s orbital. For quantum number in ML, it's 0 because there's only 1 orientation. And for quantum number MS, it's positive 1/2 because it's the first and only electron. For example 2, we're going to talk about carbon. On the periodic table, you can see the electron configuration, and carbon has 1s squared, 2s squared, and 2p squared. In carbon, the outer electrons are in 2p orbitals. That means n, the energy level, equals 2. Quantum number L has 1 because p orbitals only have 1. For quantum number in ML orientation, it can be -1, 0, or +1. I picked -1 to represent one of the p orbitals, and MS equals -1/2 for the spin down electron. So each of carbon's 2p electrons will have a slightly different ML or MS to keep them unique. For example 3, we're going to look at sodium. The electron configuration for sodium is 1s squared, 2s squared, 2p to the 6, and 3s to the 1. So we know that the outermost electron is the 3s orbital. That makes the quantum number n equals 3 for the third energy level. Quantum number L equals 0 for an s orbital. Quantum number ML equals 0 because there's only 1 orientation. And the quantum number MS gives us a +1/2 for the single unpaired electron. Understanding electron placement and energy helps nurses grasp how ions like sodium, potassium, calcium, and chloride behave in the body. Without knowing about quantum behavior and electron energy levels, we couldn't understand how ions form or interact in IV fluids, electrolytes, and medications. Now we're going to move on to topic 4, electron configuration. Electron configuration is the way we describe how electrons are arranged around the nucleus of an atom. Each electron occupies a specific energy level and orbital, kind of like seats in a stadium where no 2 electrons can sit in the same spot. Understanding electron configuration helps us predict how an atom behaves in a chemical reaction, especially how it bonds with other atoms. Electrons fill the orbitals in a specific order based on 3 main rules. 1, the Aufbau principle, which electrons fill the lowest energy levels first before moving to higher ones. 2, the Pauli exclusion principle, where each orbital can hold a maximum of 2 electrons with opposite spins. 3, the Hund's rule, when electrons fill orbitals of the same energy, like the 3p orbitals, they fill 1 in each first before pairing up. For example 1, we're going to talk about hydrogen. Hydrogen has 1 electron, so it fills only the first orbital, the 1s orbital. The electron configuration is simply 1s to the first power. This means that hydrogen has only one electron and the 1s energy level. In the real world, hydrogen's simple configuration helps explain why it easily bonds with other atoms. Like, for example, in water, each hydrogen shares its electron with oxygen to fill its shell. For example 2, we're going to talk about oxygen. Oxygen has 8 electrons, and we fill them in order of energy levels from 1s squared, 2s squared, and 2p to the 4th. That means 2 electrons go in the 1s orbital, 2 in the 2s orbital, and 4 in the 2p orbitals. In this diagram, you can see how the electrons fill the p orbitals. Each box is an orbital, so px, py, and pz. Electrons fill one in each box first, then start to pair up, which is why 2 electrons end up unpaired. These 2 unpaired electrons explain why oxygen forms 2 bonds, like in H2O, because it needs 2 more electrons to complete its outer shell. Now for my third example, let's look at calcium, which has 20 electrons. Using the order of orbital filling, we place the electrons like this. So 1s squared is 2 electrons, 2s squared is 2 more, which equals 4. 2p squared is 6 more, which the total will be 10. 3s squared is 2 more, the total will be 12. 3p to the 6 is 6 more, total is 18. And 4s to squared is the last 2 electrons, and total will be 20. So the full configuration is 1s squared, 2s squared, 2p to the 6, 2s squared, 3p to the 6, and 4s squared. Or shorthand, AR 4s squared, using the noble gas argon as the core. This tells us calcium's 2 outermost electrons are in the 4s orbital. These are valence electrons. Valence electrons are the ones involved in bonding and in chemical reactions. Calcium tends to lose those 2 4s electrons to become calcium ion with a 2+ charge, which gives it a stable noble gas configuration. So these are the valence electrons, and all of them are filled to 4s orbitals, with the 4s box containing 2 paired arrows. Electron configurations helps explain how atoms form ions, and that's really important in nursing. For example, sodium, potassium, and calcium all lose electrons to form positive ions, and those ions are what our bodies use for nerve impulses, muscle contractions, and heartbeats. The reason these elements form ions so easily is because of their outer electron configurations. They lose electrons to reach a stable noble gas state. So understanding electron configuration helps nurses understand why electrolytes are vital and how imbalances can affect patient health. Now we're going to move on to topic 5, Lewis dot structures. Lewis dot structures are a simple way to show how valence electrons, the outermost electrons, are arranged around atoms and how they're shared or transformed when atoms bond. This helps us predict the shape, bonding, and stability of molecules. Each dot in a Lewis structure represents one valence electron, and the goal is for atoms to reach a stable configuration, usually with 8 electrons in their outer shell, which we call the octet rule. Since there are 5 basic steps to drawing a Lewis dot structure, we're going to use example 1 to show how to do it. So for step 1, we count the total number of valence electrons in all atoms. For this example, we're going to use carbon dioxide. Since carbon dioxide is a compound, we have to look at carbon and oxygen. Carbon has 4 valence electrons and oxygen has 6. So since carbon has 4 valence electrons and oxygen has 6, we're going to add those together. But since there's 2 in oxygen, we're going to multiply that and we're going to get 16. That would be 16 valence electrons. For step 2, we choose the central atom, which is usually the one that can form the most bonds and often the least electronegative. So for our Lewis dot structure, we're going to put carbon in the center because it forms the most bonds. For step 3, you place single bond lines between atoms to connect them. Then since we have 2 oxygens, we're going to put oxygen on the outer sides. And then we're going to do the math because this is 2, 4, so we're going to subtract. And now we only have 12 left. For step 4, we add the remaining electrons as lone pairs to complete the octet rule. So we have 12 left, so we're going to do 2, 4, 6, 8, 10, 12. For step 5, we have to check the structure, and we have to make sure all the atoms have 8 electrons. Since our central atom only has 4 electrons, including these double bonds right here and the 2 that it already has, it needs a total of 8. So we have to take from the oxygen. So now we will have double bonds on each side so that carbon can have a total of 8 electrons. And this will be the final for carbon dioxide. Moving on to example 2, we're going to draw a Lewis dot structure for a polyatomic ion. We're going to work on a compound. This is the compound we're going to be working on, NH4+, which is ammonium ion. So first we're going to find the valence electrons for N and H. On the periodic table, we see nitrogen has 5 valence electrons, and hydrogen only has 1. Now we want to add this all up, so 5 plus 1 times 4 equals 9. But since we have a positive charge, that means we must subtract 1 from it, and we'll have 8. Now our central atom is nitrogen, so we're going to put nitrogen right in the center. Now we want to place the 4 hydrogens, so 1, like so. Now there's 2, 4, 6, 8, and we subtract 8, and now we have 0 left. This means there are no electrons left to place as lone pairs. Now for step 5, we're going to check for the octet rule. Each H has 2 electrons around it, and nitrogen in the middle has 8 in the bonds around it. So nitrogen has 1, 2, 3, 4 bonds, meaning that it has a total of 8, which satisfies the octet. Now we want to check for the formal charge of each atom. So nitrogen has 5 valence electrons, 0 non-bonding / lone pairs, and 8 bonding electrons. So now we want to find the formula, and the formula is valence So the formula for formal charge is valence electrons minus non-bonding electrons minus bonding electrons divided by 2. So when we plug that in, we get 5 minus 0 minus 8 over 2. Then that will give us 5 minus 4, and that will equal the plus 1. So nitrogen has a plus 1 formal charge. So for hydrogen has valence. So hydrogen has 1 valence electron, 0 non-bonding, and 2 bonding electrons because each H forms 1 single bond. Now we plug that into our formula, so 1 minus 0 minus 2 over 2, which also equals 1 minus 1, and that'll give us 0. That means each hydrogen has 0 formal charge. Now we're going to move on to example 3. Example 3 wants us to identify the type of bond for the following below: CO bonds in carbon dioxide as ionic, polar covalent, non-polar covalent, or metallic. First, we're going to use this Pauling scale to find the electronegativity values. The scale tells us carbon C has 2.55 electronegativity and oxygen O has 3.44 electronegativity. Now we want to compute the electronegativity difference. So we subtract C from O, and we get 0.89, meaning the electronegativity difference is 9. So we want to look at the usual cutoff ranges, and we see that our bond is 0.89. 0.89 is not in between 0.0 and 0.4, so it's not non-polar covalent. It's not 1.7, but it is in between 0.5 and 1.7, so it is polar covalent. So each CO bond is polar covalent. In nursing and health sciences, Lewis-dot structures help us understand how molecules form and interact in the body. For example, water, or H2O, has a bench shape and polar bonds. That's why it's such a good solvent in the body. Carbon dioxide, CO2, is produced in cellular respiration and is released from the lungs. Its double bonds make it stable but easily exchangeable in the bloodstream. And oxygen O2 has a double bond which attaches to the hemoglobin to carry oxygen through the body. These structures help nurses understand acid-base balance, gas exchange, and drug interactions, since all of those depend on how atoms bond and share electrons. Now we're going to move on to topic 6, VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. It's a simple model that predicts the shapes of molecules by assuming that electron groups, bonding pairs, and lone pairs around a central atom repel one another and arrange themselves to minimize that repulsion. Molecular shape matters because it affects polarity, solubility, reactivity, and how molecules interact with biological receptors. All things nurses care about when thinking about drugs, fluids, and biochemical reactions. There are 5 steps to predict shape. I'm going to use example 1 to show you. The first step is drawing the Lewis structure. For this example, we're going to do boron trifluoride. For step 1, you must draw the Lewis structure. So when we do the math, we have 24 valence electrons total. When we place these down, 2, 4, 6, we subtract 6 from there, and we get 18. Once we distribute the lone pairs, we have no more. And since boron has 8 electrons around it, that means that it's good. For step 2, we count the electron domains. There are 1, 2, 3. So 3, Step 3 is to determine the electron domain geometry. On this table, you can see that this resembles this one. with no lone pairs. So our electron domain geometry is trigonal planar. For step 4, you must adjust for lone pairs to get molecular shape, but here you see we have no lone pair, so therefore our molecular shape is also trigonal planar. For step 5, we must identify bond angles and polarity. If we go back to our chart, we can see that the trigonal planar has a 120-degree bond angle. Therefore, our bond angle is 120 degrees. This molecule is a nonpolar overall because the bond dipoles are symmetrically arranged and cancel each other out. So our polarity is non-polar. Now I'm going to move on to example 2. For example 2, we're going to use the Vesper theory on sulfur dioxide. So first we're going to find the valence electrons of sulfur and oxygen. On the periodic table, sulfur and oxygen have both 6 valence electrons. Once we do the math, we get 18. Now we're going to draw the Lewis structure, and we're going to put sulfur as the central atom. So since there's 2 oxygens, we're going to put oxygen around it. Now that's 2, 4, so we subtract 4 and we get 14, and now we distribute the rest. 2, 4, 6, 8, 10, 12. Now we have 2 left, so we're going to put that on top of sulfur. Now the problem here is that sulfur only has 2, 4, 6 electrons around it, and the rest have 8. So we're going to add a double bond here and remove this so that they share this electrons. And to make this even, I'm just going to remove that side too and put that there so they share it equally on each side. Now for step 2, we count the electron domains. So we have 2 bonding pairs and 1 lone pair. So we have 3 electron domains. Now we must determine the electron domain geometry. Since sulfur has 3 regions of electron density, 2 bonds, and 1 lone pair, it makes it trigonal planar. Therefore, the electron domain geometry is trigonal planar. Now for step 4, we must adjust for lone pairs to get molecular shape. Now for this, we have 1 lone pair, and we are trigonal planar, so it will be bent or angular. Now if we look at the actual Lewis dot structure of sulfur dioxide, you can see that the angle is slightly less than 120 and around 118 because the lone pairs push the bonds closer together. So our bond angle is less than 120 degrees, more specifically like 119 or 118 approximately. It is polar. So sulfur dioxide is polar due to its uneven pool of electrons, and it has a bent shape and an unequal charge distribution. Now I'm going to move on to example 3. We're going to use the Vesper theory on phosphorus pentachloride. So we need to find the valence electron for phosphorus and chlorine. So phosphorus has 5 valence electrons and chlorine has 7 valence electrons. When we do all the math, it'll bring us to 40 valence electrons. Now we're going to draw the central atom, which is P for phosphorus. So there are 5 chlorines, so 2, 3, 4, 5. Now that is 2, 4, 6, 8, 10. So we subtract 10 And now we have 30 valence electrons left. Now we distribute our 30, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Now we're just going to subtract the 30, and now we have 0 valence electrons left. Now we're going to count the electron domains. So there are 1, 2, 3, 4, 5. 5 electron domains. Now we must determine the electron domain geometry. And if you look on the graph here, we can see that this has 5 electron domains, and so does this one. So this means that our answer is trigonal bipyramidal. Now for step 4, we must adjust the lone pairs to get a molecular shape. But since there are no lone pairs, it will still be trigonal bipyramidal. Now for step 5, we must identify bond angles and polarity. Since our geometry is trigonal bipyramid, it is 90 degrees between axial and equatorial, and 120 between equatorial bonds. And the polarity is a non-polar overall because it is symmetrical and the dipoles cancel out. In nursing, Vesper theory matters because molecular shape is directly related to the function and interaction. Trigonal planar molecules like boron trifluoride are flat and often act as electron pair acceptors, which is a property seen in some drug intermediates and metabolic reactions. Bent molecules like sulfur dioxide behave similar to polar molecules like water, and they dissolve easily in the body fluids and can influence acid-base balance when inhaled or absorbed. Molecular geometry helps nurses understand drug solubility, gas exchange, and how medications interact at the molecular level. Finally, for topic 7, we're going to talk about chemical nomenclature of molecular and ionic compounds. Chemical nomenclature means the systematic way we name chemical compounds so scientists all over the world can identify them without confusion. So basically, it's a universal language that focuses on 2 main categories, which is ionic compounds, which are made up of metals and nonmetals, and molecular or covalent compounds, which are made of nonmetals. Ionic compounds form when a metal transfers electrons to a nonmetal, forming positive and negative ions that attract each other. We name them by the metal, which is the cation, is written first, and the nonmetal, the anion, name comes second, with this ending changing to IDE. And if the metal can form more than one charge, like transition metals, we indicate the charge with Roman numerals. For example, when we're going to talk about sodium chloride. Sodium is a metal, and chlorine, is a nonmetal. Sodium forms a positive ion, and chlorine forms a negative ion. So the charges balance each other out. For example 2, I'm going to show you a prefix chart, which is mono, di, tri, tetra, penta, and hexa. For example, mono is used in carbon monoxide, but mono is only used for the second element and not the first. Di is used in carbon dioxide. Tri is used in nitrogen trihydride. Tetra is used in carbon tetrachloride. Penta is used in diphosphorus pentaoxide. And hexa is used in sulfur hexafluoride. What also is important to know is that the second element's name always ends in IDE, IDE. 3, we're going to talk about iron chloride. So according to our periodic table, iron is in the middle right here, and these are transition metals. So iron is a transition metal. Since it's a transition metal, it means that it can form more than one charge. And chlorine over here is a nonmetal, meaning it'll always have a -1 charge. And here we know there are 3 total chlorides. That means there's a negative charge of 3. To balance the -3 charge, Fe must be +3. So the cation is Fe3 positive, and the compound is FeCl3. We write the name as iron 3 chloride, where the 3 Roman numerals shows the metal's charge. So we know the Roman numerals equals the positive charges. Therefore, our ionic compound will look something like this. Fe3 positive in the middle and 3 chlorines around it. Nurses use chemical nomenclature not just to memorize names, but to help us understand what's inside medications and solutions we use daily. For example, NaCl, or sodium chloride, is used in IV saline solution. Iron 3 chloride is an iron supplement. CO2, or carbon dioxide, is used for respiratory gas. So recognizing the names and formulas lets nurses safely interpret lab results and recognize compatible ID additives and understand patient chemistry. And that was the last of my video. Thank you for having me. Have a great day.